actually, a lot of what we're doing is leveraging the principles of electronics that you guys will have been familiar with for in the industry for 70 years, and we're applying those same principles into new systems using additive manufacturing and actually developing this interface, cyber-physical interface between electronic processing and physical processing. I'll explain what I mean by that as we go. So, I'm a biologist by background. If electrons were the substrate of the last 70 years, biology is going to be the substrate of the next 70 years. And the reason I believe that to be true is that we have to be able to operate in a much more sustainable way on the planet. And biology offers the potential to, what we say, feed, fuel, heal, build, compute, by being able to process biology in completely new ways that we weren't able to before, but leveraging the principles from the electronics sector. So you're familiar that biology, you have DNA, which is a code. That code is programmable. So if we can reprogram that code, we can now start to generate lab-grown foods that you might be familiar with, biofuels. We can develop personalized medicines, including cures for cancer. And as I say, we can leverage the principles of electronics to do this. We're also leveraging our platform into robotics and automation as well, but I'll focus mainly on the life sciences today. So, a reminder, as if you needed it, of how important Industry 4.0 is. So there is a $3.7 trillion opportunity from Industry 4.0, but only if you think about it the right way. And electronics is a critical part of this. Now, we all know that digitization is a major theme over the next 10, 20 years. And Industry 4.0 starts to blur the lines between the electronics world and the physical world, including biology. And we're leveraging additive manufacturing, 3D printing, to develop this Industry 4.0 technology for use in processing biology. And the disruption that will come from Industry 4.0 is inevitable. And therefore, if we can apply electronics in a clever way into this new Industry 4.0 paradigm, there is huge new value to be created. So 3D printing is starting to evolve from being a prototyping technology into being a genuinely new technology that allows us to build products in a new way that didn't exist before. And I'll show you that in a second. And there are some very important principles as we manage this transition to the new world of 3D printing. We're using multi-material technology, so we can combine different types of material together. We are going to use 3D printing for the whole life cycle, not just for prototyping. And we're looking much more at functional products than aesthetic products. We have a completely digital tool chain. This is what 3D printing enables. And there's an adage that's very similar to Moore's law in additive manufacture. Because it's an additive process, complexity is free. So we can get more and more complexity into a smaller unit volume. And that allows us to start to leverage the principles of Moore's law, but in physical processing. Now, it probably helps if I just illustrate what I mean by those concepts. So, classical life sciences, you've all seen pictures of labs making vaccines and doing diagnostic testing over the last couple of years. And when you think about the footprint of those labs, they are at least the size of this unit here. And you compare that to the size of the actual biology in that lab. The biology is that big, and the infrastructure is this big. And so there's something radically out of proportion there. So classical life sciences uses lots of very sophisticated instruments and PhD scientists pipetting liquids around the lab. And in fact, what the world has really done is automate the scientist, automate the human, rather than automating the biology. And what we're about is using 3D printing and integrating that with electronics to now automate the biology in a much denser footprint. So, you're all familiar with how Kilby and Noyce developed the integrated circuit. And the integrated circuit in the late 50s was the first time that electronics had been brought together in a single integrated monolithic product. And what we have developed is the world's first integrated circuit for physical processing. So not processing electrons, but processing fluidics and biology. And the integrated circuit in electronics led to the whole information processing revolution, which started with a computer. And we were able to move away from mainframes to desktop computers, to laptops, to the phone in your pocket. And that was all leveraging the principles of Moore's law. So what we're developing is the world's first biocomputer. The biocomputer uses the same principles, but now has processing units for processing biology, so that we can recode it, we can turn it into a medicine, into a food, into a new biofuel, or even into a DNA data storage device. So using 3D printing, we're building these processes that shrink down the lab from being something the size of this room into something the size of a Rubik's Cube. So it's a lab in a box using 3D printing. And if classical life sciences has been about big labs making vaccines and diagnostics, that's a scale-up approach. What electronics has done incredibly well over 70 years is scaling out. Transistors are everywhere, and they perform common units of operation repeatedly, and this is what we want to do in biological processing. With these processors that are integrated labs in the box, we want to scale out processing and put it everywhere. So if I lift the lid on what the biocomputer looks like, it has these blue processing devices. These are ROMs, RAMs, different types of memory and input-output devices that are assembled together into a footprint. So this biocomputer product, you can feed materials into it, hit go, and it will start to produce vaccines or foods or fuels or run diagnostic tests. And so each of these blue units is produced using 3D printing. So this is, as I say, the world's first integrated circuit for physical processing, and I'll explain the interface with electronics as I go. So first of all, so we use multi-material 3D printing, so it's actually a Stratasys polyjet printer. And what that allows us to do is combine different types of materials together. So the first thing is we can combine hard and soft materials. So soft materials let us build valves directly into the system. So we can actuate valves using electronics that are integrated and use that to drive fluids around the system and process those fluids in the same way you process biology. Multi-material also includes opaque and clear. So we can actually build optical waveguides directly into the system. And using electronics, we can have emission and detection sources to be able to monitor what's going on in the system. So, you know, most of you have probably run a lateral flow test at some point over the last couple of years. Much of biology is about detecting color changes. So if we can use these integrated optical waveguides to detect color changes, we can monitor what's going on with the biology in this system. So those different materials all come off the same printer platform as a monolithic unit. As I say, we use 3D printing to assemble this. You cannot possibly manufacture something of this complexity using any other approach. So we can use this complexity, which is free, as an additive process to miniaturize labs down to this Rubik's Cube size footprint. It's computer-inspired architecture, so to explain the electronics that we use as a predicate for this, we treat the biology and the fluids in the same way that you treat electrons going around circuits. So we have in the middle memories that we can draw on, so we can pull biology out of the memory and process it. We have fluidic buses, which are similar to data buses. And you might be able to see each one of these gray units is a bioprocessing core. So in every one of these units, we can process biology, as I say, to make a vaccine or run a diagnostic test. So with this free complexity, we can get 18 of these cores in one of these small processors. And that means we could run 18 tests at the same time or make 18 vaccines simultaneously. And by the way, just to remind you, a Coke bottle full of vaccine is enough to manufacture 5 million doses. So it doesn't take a lot of processing power to produce a lot of vaccine. Now, the keen-eyed amongst you might have noticed these electronics. So at the moment, we can't use additive manufacture to assemble the conductive materials directly in. So what we do is we use a combination of flexi electronics and conventional PCBs, and we attach them to each one of these reactor cores. And that means we can use electronic detection to monitor what's going on with the biological reaction. So, for example, as cells grow and change, say you're making a cancer therapy, you take some of the cells from the immune cells from the patient, you reprogram them so that they can now identify the cancer, and you put them back into the patient, and it will cure them. But we have to be able to look at the cells as they grow and use electronics to detect the cell growth in order to produce these effective therapies. So we can have pH sensors, we can have optical sensors, glucose, dissolved oxygen, and we can integrate those very closely into these little reactor cores and detect what's going on. Again, leveraging the principles from the electronics industry, we have developed standardized architectures that are software configurable. So in the same way you might have a CPU in a computer, or a GPU, or a ROM, or a RAM, we can define these hardware units and use software to configure them to different applications. So in the same way we can use software to tell our CPU to run Excel or PowerPoint, we can use software to tell our bioprocessor to produce a vaccine, or to produce a food, or produce a fuel. And that's really important. You know, one of the reasons Moore's law was so successful in electronics was that with standardized hardware, you could sell it everywhere. So the 4004, the classic first general purpose computing chipset, was standardized hardware architecture that was software configurable, programmable, and therefore you could use it in many locations. And therefore you can access economies of scale that weren't available previously. So we're trying to leverage exactly the same principles. So all of the 70 years worth of knowledge and development that's gone into those devices, we're now amplifying up into the physical processing device. So there's a very close coupling between the electronic processing and the physical processing. So this is what Industry 4.0 is all about, the blurring of the lines between the cyber and the physical. Because we have so much electronic sensing going on, this is an AI-able device. So we can start to use machine learning on the data sets that come off this bioprocessor to be able to drive it in new ways, learn new ways to process the biology, and access that computing power in a way that we can make vaccines quicker, we can make these new foods more accessible. And then we can start to network these devices together using the Internet of Things type principles, so we can start to coordinate how these devices perform. So in the same way that the integrated circuit allowed us to put electronics everywhere, I mean, you cannot look somewhere and not see electronics. We can start to put bioprocessing everywhere. So if conventionally all of biology was done in a lab, we can now start to take it into some completely new places. So we're already starting to use our biocomputer device in a therapy manufacturing process. So in this case, it's making a particular antibody that's used as a therapy. This is a slightly clearer case. So this is a hospital bed. As I've described, some of these cancer therapies, cancer has grown, it's evaded your immune system hasn't been able to kill it. We can take immune cells out of the patient, we can use genetic reprogramming to recode the cells so they'll identify the cancer, we put them back in, and you can cure the patient. Now, classically, that takes 14 days in some centralized location in a big lab. But with this new bioprocessing capability, we can, in electronics, you do distributed computing, we can do distributed biocomputing. So we can make the therapy by the bedside. We're completely agnostic as to where the therapy is made. And then another relevant example up here is we can start to do pathogen detection on planes. So if aviation was a major cause of the spread of COVID because of international travel, then that's a very valuable location to detect new pathogens being transmitted internationally. So we have a grant and we're up and running on this already to develop the ability to sample from the air in an airplane and detect pathogens, whether it's an engineered pathogen or a variant of COVID or some other potential pandemic disease. And we can repeatedly sample the air and detect these pathogens in the course of a flight. And again, this is enabled by these bioprocessors that we can put anywhere. Now, of course, the data and the telemetry that comes off the electronic sensing in those devices is critical, because we can now start to use machine learning algorithms to detect these pathogens as they're dispersed around the world. And we can build this machine learning model of pathogen being spread, and therefore we can come up with plans to mitigate. So if we can distribute biocomputing, electronics and biocomputing everywhere in this interconnected network of devices, we start to have the potential to real-time detect new diseases as they're arising in a geography, and in exactly the same platform, using the same electronics and the same processing devices, we can now software configure those to make the vaccine in response to that pathogen. And vaccines technically only take about 2 weeks to be able to synthesize and create. Therefore, if we can detect a pathogen early enough, we can produce a vaccine quickly enough, you can stamp out that infection at source and prevent it ever spreading. And quite deliberately, this is not only earthbound technology. If we can distribute the electronics and the physical processing anywhere around the Earth, we can start to take it out into space and onto Mars as well, because the principles of Moore's law in electronics and in physical processing apply equally well here as they do out in other environments. And we're starting a program with the UK Space Agency to put these technologies onto satellites, and therefore we can start to process biology in new ways out in space as we develop those capabilities. So, as I say, I've mentioned it a few times, we're leveraging the principles of Moore's law in physical processing. So what we need is the intersection of the electronics and the physical processing devices, all under common architectures and operating in similar ways. And because this is a digital platform, we can iterate our development extremely quickly. So we can integrate new types of electronic sensors as they're developed. We can very quickly conform using 3D printing our processors and embed the very latest electronic technologies. Like the evolution of Kilby's first circuit, it may have started off with a few gold wires and only 5 devices in it, but the fact you could integrate all of these together and start to produce them as monolithic units unlocks 70 years worth of Moore's law. And as I say, additive manufacturing allows us to produce that level of complexity for free. So if in electronics transistors are free, we can produce physical devices where that complexity is free. So what we're doing is working with our partners to develop the core capabilities for physical processing, and then we develop application-specific chipsets. So we're already working with partners developing cell therapies or developing machine learning models for how you manufacture biology at different scales. And the more people sign up to this digital platform, the better it gets. So the core gets better, the applications get better. And we can iterate the generations of these architectures very rapidly using this digital toolchain. Again, like the semiconductor sector, where you have common architectures that are available using software to many different applications, we're applying the same principles. So this is actually a slide borrowed from ARM, and one of the founders of ARM is joining our board very shortly. So what they have done is build this ecosystem of technology partners, and then they work together to take the ARM processors out to OEMs, and those common IP blocks are used to access many different technology areas. Well, again, similar principles for us. We've built a technology ecosystem which includes some of our 3D printing partners, data aggregators, biology partners, hardware partners. we integrate these technologies together, we combine the electronics, the 3D printing together into these architectures, and the common architectures have already given us footprint. We're only 18 months old as a company, but they've already given us footprint in bioprocessing, in diagnostics, biofuels, new biosurveillance capabilities, pathogen detection on planes, all leveraging the same architectures. And we've been lucky enough to win 8 grants so far, which I think is one ahead of Rolls-Royce, so we're not doing too badly. And then just to close, I was saying this, we're actually a profitable technology development company. So we've done everything ourselves so far through grants and through customer work. And we've made our platform available to commercial partners to come and develop these new products together. So it's an open platform that people can come and work with us. And we hope in your case that we will be able to integrate new electronic capabilities. We can rapidly adapt the 3D printing processes to accommodate these different types of sensors. We want to develop more machine learning capability. So we're very open to partnering with people who can bring technologies to bear as part of our stack to tackle this new world of bioprocessing. So, please do go on our website, biologic-tech.com, or drop us an email into that info box, scan the QR code, however you want to grab me, or otherwise I'll be here for a few minutes afterwards as well, and we'd love to talk in person. But we want to thank the electronics industry for giving us a 70-year roadmap, so we know what the next 70 years looks like for what we're trying to do, and we look forward to partnering with you guys. Thanks so much.